English സംസാരിക്കണമെങ്കിൽ പറഞ്ഞാൽ മതി. ഓക്കെ, ഇന്നത്തെ ടോപ്പിക്സ് എന്ന് പറയുമ്പോൾ ഇൻട്രൊഡക്ഷൻ ടു ടെൻസർ ഫ്ലോ, പിന്നെ അത് കഴിഞ്ഞിട്ട് നമ്മളൊരു സിമ്പിൾ ആയിട്ടുള്ള ക്ലാസിഫയർ ഉണ്ടാക്കും, ഡിജിറ്റ് ക്ലാസിഫയർ. അത് കഴിഞ്ഞിട്ട് പിസ ആണോ അല്ലേന്ന് ക്ലാസിഫൈ ചെയ്യാൻ പറ്റുന്ന ഒരു ബൈനറി ക്ലാസിഫയർ ഉണ്ടാക്കും. ആൻഡ് ഫൈനലി 100 ഡിഫറെൻറ്റ് ടൈപ്സ് ഓഫ് സ്പോർട്സ് ക്ലാസിഫൈ ചെയ്യാനുള്ള ഒരു മൾട്ടി ക്ലാസ് ക്ലാസിഫിക്കേഷൻ മോഡൽ ഉണ്ടാക്കും. അപ്പോൾ നമുക്ക് ആദ്യം ഗൂഗിൾ കൊളാബ് നോട്ടിലോട്ട് പോവാം.
ഒരാൾക്ക് ഇംഗ്ലീഷിൽ കമ്മ്യൂണിക്കേഷൻ വേണം എന്നാ പറയുന്നത്.
ഓക്കെ ഓക്കെ. Okay, we'll start with TensorFlow. What is TensorFlow? TensorFlow is an open source machine learning library developed by Google Brain's team. Basically, it is a framework that we can use for deep learning applications. It will make our job way easier than writing code from scratch. TensorFlow basically uses TensorFlow 2.0 basically uses Keras on top of it. So Keras is easy to understand. The code is easier to understand than other types of deep learning frameworks. It is also okay. So flexible, efficient, and intuitive. So let's start with what we are going to do this time. We'll load a pre-built data set, and that is going to be the MNIST data set. Then we'll build a neural network that classifies images. We'll train this neural network and evaluate the accuracy of the model. Okay, first of all, we'll import TensorFlow as TF. Okay, we don't really have to use TF as the name, but we can use that is the standard name used for TensorFlow. So we'll do the same. We'll use Matplotlib to visualize the images. So next we are getting the data set. So Keras also have built-in data sets. We are going to use one of that. Okay, so MNIST data set. MNIST data set is a data set containing images of digits like from 0 to 9 and their corresponding labels. So the size of the data set is 60,000. Basically, there are 60,000 different images in the training data set, and for testing data set, I think there is around 10,000 different images. So first we'll talk about how images are represented in computers. They are represented using different grayscale images are represented using values from 0 to 255. Why 255? Because they are represented as 8-bit digits, as represented in 8 bits. So since the index starts from 0, it will be 0 to 255. Okay, so different shades of gray will have different colors. Let's see. This shade of gray has a number of 95. Okay, this the black color will be 0, and the most brightest color will be 1. Sorry, 255. Okay, all the shades in between will have different grayscale values. So this is how images are represented in computers. They are represented as numbers. A two-dimensional array. We can in mathematics we call that matrix. So everyone knows about that, right? Okay, so we'll first visualize. We'll first see how like array images are represented inside the data set. So just like this, the images are represented in values between 0 and 255. So they are in NumPy array format. As you can see here, the type will be. Okay, so NumPy arrays have different shapes. If the input shape is, it is just a value that is integer value or some other kind of value, then it will be, the shape will be bracket nothing. So it is a rank 0 tensor. Tensors are you can call it as a generalization of arrays or matrices. So this will be a rank 0 tensor. If you are going to pass in an array, that will be a rank 1 tensor. Similarly, if we pass in matrix, that will be a rank 2 tensor. So images are represented as basically rank 2 tensors. Grayscale image, that is. Color images are represented as rank 3 tensors. We'll talk about that later on. Okay, so the shape of X-train. All the images in our data set are of the shape 28 by 28. That is 28 by 28 pixels, 28 rows and 28 columns. So since there are 60,000 images, the shape of the X-train will be 60,000 by 28 by 28. Similarly, if we take just one image, the shape of that will be 28 by 28. Then white train. The shape of white train. White train is our labels. So there are 60,000 images and their corresponding labels. So there are 60,000 labels. Okay, if we take the first label, we'll get 5. Our first image is actually 5. So we'll visualize that later. We'll visualize that now. Okay, so first image, X train of 0, 0th index, and Y train of 0th index will be the title. So this is our image and this corresponding label. Uh, since machine learning, no, deep learning models actually requires us to input scaled values, we'll divide each X train and X test by 255. So our output will be of the range output of the range 0 to 1. First of all, I have to do this. We can see all the values that were previously 0 to 255 are now from 0 to 0 to 1. Okay, we can check that like this. The maximum value is 1 and the minimum value is 0. Okay, next we are going to build the model. Okay, so our model is going to look like this. We'll have an input layer. Then we'll flatten the images. By flattening, we mean there are 28 by 28 pixels. So 20, the dimensions of the images are 28 by 28. So the total number of pixels in the image will be 28 into 28. That is 784. We'll basically flatten out the images. Instead of 2D array, we'll make it 1D array. So that's what flatten is going to do. Input shape is 28 by 28. That is our expected image shape. Next is dense layer. Dense layer is fully connected layer. Yes, as explained earlier, explained last day, all the input, all the okay, the weight will be connected from all image, all pixels in previous layer to all the neurons in current layer. So there will be 128 units of dense. Basically, in this image, you can see if this is the input layer, there will be 128 different hidden units or dense units. Next is dropout. We'll explain that later on. And finally, this is another dense layer. The value of this is okay. In here, the value of 128 is arbitrary. We can put in any value. I just put in 128 for this example randomly. Because it had a good accuracy. Then tf.keras.layer.dense 10. Why did we put 10? Because the output shape will be okay. We are going to one hot encode the target y value. We are not going to directly do that. So Instead, if the first value is okay, if the first value is 5, then we'll convert this into a format such as this, where the fifth index will be 5, will be 1, and all other values will be 0. That is what we call as one-hot encoding. So the model will be outputting a like array like that. So that's why the final layer has 10 units. Next, we'll try predicting using the model. We didn't train the model yet. We are just going to check how the output looks. So this is how the output is going to look. There are 10 values in total. It is a two-dimensional matrix of shape, 1 by 10. There will be 10 columns and 1 row, because we are only passing the first image into the data set, into the model. Okay, next is softmax function. Softmax function equation is this. I'm not going to explain what the equation means, but rather what it does is it converts all the here logits value. This output value is called logits. So output of the network is called logits. It's going to convert from logits value into some kind of probability. So the probability of the prediction of the image being in the first image being 0 is 14%, and the probability of image being 16 is being 1 is 16%, and so on. So that's what softmax function is going to do. Okay, as explained earlier, this is how one-hot encoding looks. Uh, okay, next we are going to define a loss function, because loss functions are used as the used for training. Okay, so what do we mean by training a model? What we are going to do is the model will calculate the difference between the inputted target value and the predicted target value, and it will find some kind of loss between them. So here we are going to use categorical cross entropy. This is the equation. So this is probability of our given value, target value, that is white train, and this is the probability log of q of x. Q of x is our output of output of our model passed through a softmax function. So and we'll take the summation with respect to all classes. Uh, okay, since we are going to use, we are not going to put any activation function softmax directly into our model. We are going to explicitly state that the model's output are logits. Okay, so from logits equal to true. We are randomly calculating the loss function between the first actual value and the first predicted value. So we got 2.47 something. Okay, so before we start training, configuring and compiling the model, we have to compile the model using model.compile function. We'll have to set an optimizer that can optimize the model. Also some kind of loss function. We already defined our loss function. We don't have to make it call it differently like that. We can actually pass the same here. Okay, so the metric we are going to use in order to assess this model is accuracy. So that's our metrics. So Adam is a compiler that can work well for almost all kind of problems, and that's why we are going to use Adam here. Its full form is adaptive moment. It uses some kind of momentum in order to find, in order to optimize the problem, optimize the model. So next we are going to fit the model, that is train the model. So we'll train for 5 epochs. One epoch means we are passing the whole data set for training one time. So five epochs means we are going to pass the data set and train using it 5 times. In order to train, we have to pass in the X train, that is image set of images and their corresponding labels. Okay, so this is still training. Okay, now finally we can evaluate the model. Okay, our loss is, as you can see, our loss is decreasing over time. That's what happened when you train the model. Our accuracy also keeps improving. So our accuracy in our trained data set is 0.97, that is 97%. And our accuracy in test data set is 97%. So it is a pretty good model. We can do better than this, but for now we are going to going to stop at this. So as I explained earlier, this site is a very good site in order to explain how the importance of different layers. Okay, number of layers and number of neurons. So we are going to fit our model to this data set. Basically, we want some kind of we want to classify these points, this orange color points from this blue color points. So after giving some complexity, like in our first layer, this data has totally 3 input layers. So sorry, 3 intermediate layers, 2 intermediate layers. This layer is different. It is input layer and 1 output layer. So in our sorry, all of these are hidden layers. Our output layer is not visible in this program. We have 3 hidden layers, and first hidden layer has 5 different units, and second and third has 4 different units. As you can see, our model has fitted into our data set. Our loss has decreased down. This is how the loss graph should look while training. So this is too much epochs. That's why it starts overfitting into our training data. Okay, let's go to the next problem. So pizza or not classifier. This is our next problem. So who doesn't like pizza? Okay, so we are going to classify whether the given image is that of a pizza or not, using a neural network. So we are going to create that neural network. There are around 1,000 images of pizza and not pizza. Let's see. Some images that are not pizza. And some images of pizzas. Okay, so this first code, before running it, to with this code, what we are basically doing is fetching this data from Kaggle site and downloading it into our local folder, local collab folder. So we are first we are importing necessary modules. Okay, so our data is downloaded. It's under this folder. We'll import the necessary modules. We'll import NumPy, Matplotlib for getting and plotting images, and then some TensorFlow functions that are necessary for creating the model. And this is just for reproduction. We don't need that. It's not necessary. Okay, what we are doing here is like fetching the names of all the images inside the pizza folder and also inside the non-pizza folder. So if we take the length of that, we'll understand how many images of pizza and how many images of not pizza are there. So there are, it is a balanced data set. There are equal number of pizzas and non-pizzas. As I explained in last chapter, last notebook, the grayscale images are represented using numbers. So in there are only one channel, that is grayscale channel. But in colored images, in our case, it is going to be colored images. So colored images are represented by red, green, and blue. So each of them will have different different intensity values. That is, red will be from 0 to 255, green will be from 0 to 255, and blue will be from 0 to 255. You can think of them as individual grayscale values combining together in order to form our colored image. Okay, we are reading a random image from our data set and we are checking the shape of it. So our image is of size 512 to 512 pixels, and this 3 is there for RGB, that is red, green, and blue. There will be 3 channels. That's why the 3 exist. Okay, this function is just for plotting random images from our data set. You can see it's just the image of pizza, and this is not an image of pizza, so non-pizza. Okay, first for training our data set, training this model, we'll need to get our data. So this is a TensorFlow function, image data set from directory. We imported it here. So from tensorflow.keras.utils, import image data set from directory. We can like give out the path of where the data set is, and it will fetch the corresponding data from it. Okay, labels are inferred, and label mode is binary. That is, it will be if the image is pizza, then it will be 1. The y value will be 1. If the image is not pizza, the y value will be 0. Seed is there for just for reproduction of code. Okay, this is going to be a training data, and this is going to be a validation data. Run the model. Okay, we downloaded our data set. We loaded our data set. Our training data is of type tensorflow.python.data.dops. Basically, it is a tf.data set. The tf.data.keras.data.data set object. That is what is getting returned here. Okay, so it is not an umpire array. It is you can think of it as a generator. So we have to use next function in order to get the values from it. Okay, what this is, let's see. Okay, this is okay. Here we are batching up the data set. That is every 32 images in the data and their corresponding label will be batched together. So our shape of train data will be, I can do that. Set up. Our shape of image data will be 32 by 224 by 224 by 3. Actually, it is 50 comma 32 comma 224 224 comma 3 because there are 50 batches having 32 images each, and that's what we are checking here using cardinality function. Okay, so our our values are stored in this format. So it's a tuple of values of x and values of y. So each one of the x has 32 images currently. We can try to fetch one of them. So by this we are going to fetch only the images. These are all the 32 images, and using this we can fetch the first image. This is the values of the first image. Okay. The cardinality is 50 and the cardinality of validation data is 30. Validation and test data, you can think of it as same. They are not the same, but uh, they basically do the same thing in this context. Okay. When we got the data, there were like 1966 files belonging to two classes. So we use 1573 for training. If we divide that by 1573 divided that by 32 batches, so we'll get 50. Yes, 49.15. We round that up to get 50. So that's what cardinality is about. Cardinality gives you that value. Similarly, for validation data, we'll get that. Remember how we scale the data here? Because the neural network expects value from 0 to 1 instead of 0 to 255. So we are doing the same thing here. And the code is a little bit different than before because we are using TensorFlow dataset object instead of NumPy arrays. So we have to use this map function instead of just dividing it by 255. Next is convolutional layer. Yesterday it was explained, the theory was explained, so I'm not going to explain too much. So basically does is convolves around the image and generates some kind of values. Okay, what we are trying to learn is this kernel, values of this kernel matrix. Values of input images are provided during training, and values of output is also provided. Not this output is not provided, but the target value is provided during test training. So we are our objective is to find this value during training. This is simple convolution operation, and this is the actual CNN. So instead of just kernel of 2D size, we are going to use a kernel of 3 dimensions, controlling around each depth, that is RGB, in this case RGB. So the depth will be 3. So if the depth of the image is 3, then the depth of the filter will also be 3. Each corresponding value will be multiplied and then added together to get the final result. Okay, now we can finally make the model. So a model will be convolution 2D. So okay, I didn't explain dropout yet. Wait. Dropout is a regularization method that is used for preventing overfitting. Overfitting was explained yesterday. Basically, what overfitting is, you know, after training a lot, the model will start memorizing the training data set. And that's not what we actually want. We want the model to generalize to all the data sets, not just the training data. So what we are going, what it does is, uh, by adding a random noise into the data set, we can training data during training. Um, we can expect the loss to go down, loss of the training to go up, and overfitting to go down. That is, we can prevent overfitting using regularization methods. So dropout is one of those regularization methods. The activation functions we are going to use is ReLU, that is rectified linear unit. It was explained last day. So there is going to be 3 convolutional layers, 1, 2, 3, followed by a flattened layer. That is, we flatten the image into 1 dimension. Sorry, 2 dimension, and finally we are going to add more dropout and a dense layer, followed by dense layer, some dropout, and finally a sigmoid layer. In our previous example, we used sigmoid, but um, it was softmax. Okay, my bad. Sigmoid is another function that gives us the probability. We use sigmoid when our output is binary, that is 0 or 1. It will give us a value. We are only expecting one value here this time, either 0 or 1. So we only need one unit. So this neural network will give us a value from 0 to 1, any value between 0 to 1. This is how our model looks, total 21 MB. We can finally start training our model. So we are going to use binary cross entropy. Instead of we used cross entropy earlier on for categorical cross entropy last time. We are using binary cross entropy. They are different algorithms, but essentially they do the same job of what making the model learn. The metric we are going to use is accuracy, same as before. Optimizer is also same as before, Adam. And finally, we are going to train our model. This might take some time, so I'm going to start explaining the things after that. Okay, so this history object, okay, this history will return us uh, the loss that was calculated in between each epochs for the training and validation data. So what we want is some kind of graph like this. What we expect is some kind of graph like this, where this is model complexity, and this is loss. We want a model that has low loss, training loss, and also generalization loss. What we most importantly want is less generalization loss rather than training loss, because if the training loss alone is too low, then we can then that model is actually overfitted. So that's what is shown in this image. The training loss is way lesser than generalization loss. That is, generalization loss, you can think of it as validation loss. If it is way lesser than validation loss, then it is overfitting. If they are close enough, then it is optimum. And if they are if the model complexity is too low, then both of the loss will be high. If that is the case, then it is underfitting. Okay, so optimally we want to train our loss graph to look like this. The validation accuracy or validation loss, both. Actually, loss function is that opposite of accuracy. We'll see that later on. We want our validation accuracy to be very close to our training accuracy. It should not be way down here. So validation accuracy is way down here, like example of this blue instead of green. Then it is we can conclude that our model is overfitting. For training accuracy is also way down here. We can conclude that it is underfitting. Okay, so model has stopped training. We can now visualize our plots. As you can see, our training loss is decreasing gradually. Our validation loss is also decreasing gradually. So we stopped around 20 epochs. That is, we showed our training data. We trained with our training data 20 times. And similarly, our accuracy also started increasing. Um, okay, so our validation accuracy also increased corresponding to our training accuracy. So this is a good loss graph, and this is a good accuracy graph. We can conclude that our model is pretty good with this. Okay, now so our model is ready. Now we can use it to predict some images and check whether it is actually predicting right or not. As you can see, this is an image of pizza. I got it from here, so it's a random image. You can also check using some online images after downloading it. It is currently predicting it as pizza, so we can conclude that our model is pretty good. Okay, now let's head on to our next problem. This is our image classification, multi-classification problem. So we are going to use this dataset from Kaggle, 100 sports image classification. Okay, there are going to be 100 different kinds of sports, and and we are going to classify them based on their images. Okay, this air hockey, axe throwing, bike photo, billiards, etc. Okay, same as before. Wait, I'll have to disconnect in order to use that. Okay, this is the code I'm going to use in order to fetch our data from Kaggle. So in order to know how this code actually works, you can check out this link. You need a Kaggle account in order to use the Kaggle dataset, and this Kaggle.json is basically their API, authentication API. This is a pretty good big data set. That's why it is taking some time to load. Okay, now it is downloaded. Here is our data. It is separated into test train and validation. So inside inside train, we can see that there are 100 different types of data. Sorry, 100 different types of sports, and each sports have their corresponding images in JPEG format. Okay, just like before, we are going to import our necessary libraries. Just like before, we are going to set our seed for reproduction of code. This is in order to make sure that if you are running the same, the same, collab notebook, then you'll get the same model after training as me. So it is not necessary actually. Just added it for reproducibility. Okay, let's see what all sports are there. These are the 100 sports in our data set. So football, shuffleboard, bowling, etc. We are going to visualize some images. And this is an image of archery. Okay. This is an image of figure skating. I fetched it from our data folder. You can put in whatever image you want, image path you want. Next, we are going to check the shape of our image 1 and image 2. As you can see, all the images are of same shape. We don't have to reshape it. So that saves some time. Next, we are going to load our data as the TensorFlow dataset object. So same as before, we are going to set seed in order for reproducibility. This time our label mode is categorical, that is one hot encoded. Just like before. In this case, we use pass categorical cross entropy. We are not going to use do the same. We can do the same, but we are not going to do the same. Wait, we are going to do the same. First, we are going to load the dataset. Our batch size is 32, same as before. Our image size is 224 by 224. Okay, test dataset cardinality is 16. Train dataset, there's going to be 422 batches, each batch containing 32 images. So a total of around 13,492 images in our training set. In our test set, there's going to be around 500 images, and in our validation set, there's going to be around 500 images. Next, we are going to visualize how the image looks as NumPy arrays. Okay, we can use this as NumPy iterator in order to make this dataset object into an iterator, and then we can use next in order to get the value from this iterator. So the shape of image is 32, 224, 224, 3. 32 is our batch size. And similarly, our label is 32 by 100 because there are 100 different spots here, and they are one hot encoded. We can visualize some images randomly from our dataset. Here, okay, I had Polo. Okay, creating the model. Okay, unlike before, we are not going to create a model from scratch. Rather, we are going to use transfer learning. Okay, so transfer learning is basically imagine you are trying to teach a friend a new sport, say basketball. Now, if you have played basketball yourself, you already know the basics, how to shoot, dribble, pass, and defend. So instead of teaching your friend from scratch, you can use your knowledge to help them learn faster and more efficiently. That's essentially what transfer learning does in machine learning. It takes a model that has already learned something, let's call this base model, and applies it to a new but related task. Transfer learning can save time, use less data, and improve results compared to generating like creating a model from scratch. And the transfer learning model we are going to use is different examples of the transfer like pre-made models that we can use in TensorFlow. There are many other models we can also use. We are going to use MobileNet V2. So this is how we use MobileNet V2 from TensorFlow. The actual code is it is from this directory tensorflow.keras.application import MobileNet V2. Inside MobileNet V2 object, we'll get our actual MobileNet V2 model. So we are the input shape of our image is 2224 2243. That is 224 by 224 pixels of RGB. Include top is equal to false means the last layer won't be there. our final prediction layer. We are going to create our own final prediction layer. Then we are not going to actually find, change the weight of this mobile net model. Rather, we are going to get the output from this model. We are going to pass the data into this model. We'll get the output, and using those output, we are going to pass into our custom model, sequential model. Then with that, we'll try to classify this 100 different spots. So the mobile net is downloaded, and we set each layer trainability into false. Here is how mobile net actually looks. It's a big model, relatively big model, but it is actually quite efficient compared to other models. That's why I used it. Okay, so MobileNet V2 expects some kind of pre-processing. In our case, we already did this, but just to be sure, we included this. We don't have to, but we include this. This lambda function basically turns any Python function or any other actual normal function or TensorFlow functions into a layer. So that's what this code does. This is MobileNet, our MobileNet layer. Our input passes through this MobileNet layer, and output of that goes to a global max average pooling. Okay, this is how global max average pooling works. Yesterday, max pooling was explained. So global max average pooling is basically taking the averages of all value uh, uh, with respect to different output. Can show you here. So our mobile net output shape is 7 by 7 by 1280. That is, there is going to be 1280 units or channels by the end of uh, uh, in the output of mobile net. So for each channel, it is going to be 7 by 7 image. So like this, 7 by 7 instead of this dimension. So what it basically does is takes the average of all the values inside that 7 by 7 image, and that is returned as compressed features. So basically, the all the average of the 7 by 7 is taken. Hence, we get this output shape. None 1280. 1280 is dense. Sorry, channel number of channels here. We pass that onto a dropout function. Dropout is used for regularization in order to prevent overfitting. Okay, dropout is followed by a normal dense layer. There is going to be 512 units using activation function ReLU. And finally, we are going to use softmax function in order to find the probability between different classes, the 100 different classes. And dropout is used in between in order to prevent overfitting. If we are finally going to train our model, it is going to take a while. That's why I started training early. Okay, mobile. Our optimizer is going to be Adam. Our loss is categorical cross entropy. Same as this, but the difference is the input won't be of an array. Our input is already one hot encoded, so we can directly pass categorical cross entropy instead of sparse categorical cross entropy. If our input target value is not in one hot encoded shape, then we will have to pass sparse categorical entropy, but not in this case. Okay, in our metrics is accuracy and F1 score. So you can see this is how training works. So it might take a while. We'll explain the rest. The same output is going to be there, so I'm not going to run this code. Here, as you can see, just like I explained in last notebook, we expect our loss to look like go like this, go downwards while training, and we expect our validation loss to be close to our training loss. So in here, our validation loss is close enough to our training loss. Training loss keeps decreasing until around 0.2 something. In the case of accuracy, our training accuracy is around 94 something, and our validation accuracy is also pretty close, 92 or 92 something. As you can see, our training accuracy keeps increasing while during each epoch, and our validation accuracy is also close to our training accuracy. So it shows that it is not overfitting. And finally, we evaluate our test data. After evaluating, we get that our model accuracy, our what accuracy is model accuracy is 94.19, that is 94 percentage in our test data. Test data is data that our model has never seen before. Same goes to validation data. So from this we can understand that our model is actually pretty good. It can load in any data, so it can understand which spot it is given any image. This is our F1 score. F1 score is also pretty high, 94. So our model is pretty balanced with respect to its precision and accuracy. Okay, this is our Y prediction looks. Not we are going to use np.argmax. Our actual Y prediction is going to be one hot encoded values. When we use np.argmax, it is going to fetch the probability index of the index of the class having the highest probability. So in the first case, after prediction, the 81st row, 81st column had the highest probability. So 81 became the index. Okay, similarly, we can see the classification report, accuracy score, reference score, and confusion metrics using sklearn.metrics library. So accuracy score, we can pass in the Y true value. Y true is basically the target value that we are expecting from test image, that is test data. Y true value is the value we know. Y prediction is the value that the model predicts. So we are going to check how right it is using this accuracy score function, and it returns 94.2. We already knew that. F1 score is 91.18. The same as this. We are just using a different library for doing the same thing. Next is classification report. Before that, I'll run the rest of the code. Our model has stopped training. We'll also show how YPRED actually looks for each observation. Okay, this is our classification report. Classification report basically shows precision recall F1 score and a metric called support for each classes in our data set. There are like 100 classes because there are 100 different types of images, 100 different type of sports, and hence 100 classes. The values are pretty high for almost everything, so our model is pretty good. Okay, YPRED is 0. Wait. The value changed because I ran out of order. Finally, we are going to plot our confusion matrix as a heat map. This code is pretty simple. We can pass in any images from internet and check whether it is predicting right or not. So in this case, I randomly searched an image for tennis and gave that image into the model. So pass that image into the model and it predicted tennis correctly. You can see the confusion matrix. The column values are way higher than other values. So our confusion matrix is pretty good. This is how y value, y pred value looks. So since y pred of 1 is 43 now, okay. The 43rd value is actually greater. So I ran it out of order. Okay. Similarly, we can pass in another image if we want. So another sport, football. This prediction was wrong, but as you can see, the prediction can also be wrong. It can be due to different factors, like how the images was resized or how the model was trained, etc. We only ran for like 10 epochs, so it can be wrong. It is not like the best model out there, but it is pretty good. So we can end our session by now. So thank you.